Every story has a beginning. For our universe, that was the Big Bang, a moment 13.8 billion years ago when everything erupted from an unimaginably hot, dense point. We can trace the expansion of space back to this primordial fireball, but what lit the fuse? What happened before the beginning? This isn't just a deep question, it's a forbidden one. As we approach that initial moment, our most powerful theories, Einstein's general relativity and quantum mechanics, simply break down. The equations that describe the very large and the very small become screaming paradoxes. At this wall, at the edge of time, our understanding ends, but our most daring ideas begin. Perhaps there was no before at all, only the potential of nothingness. This isn't an empty void, but a seething cauldron of potential governed by quantum physics. In this realm, the laws of reality allow for energy to be borrowed from nothing for fleeting moments, creating a chaotic foam of virtual particles. From this foam, a tiny bubble of spacetime could have randomly fluctuated into existence. This microscopic seed, smaller than an atom, then underwent a period of hyperexpansion called inflation, stretching faster than the speed of light to become the vast cosmos we see today. Our existence, a grand cosmic accident, born from a statistical burp in the void. But what if there was no true beginning, just an endless cycle? Imagine a prior cosmos that lived its entire life, stars burning out, galaxies drifting apart into a cold, empty twilight. Then gravity, the patient architect of the cosmos, began to pull it all back together in a colossal, big crunch. As it crushed down, the rules of quantum gravity took over, preventing a final, infinite collapse. Instead of an end, there was a rebound, a great bounce that released all that compressed energy into a new Big Bang, ours. In this view, our universe is but one chapter in an epic, timeless story of cosmic rebirth. A third, and perhaps the grandest theory, suggests our Big Bang wasn't the beginning, but just a beginning. Imagine that quantum foam not as a one-time event, but as an eternal, bubbling ocean. This is the multiverse. In this cosmic ocean, new universes are constantly branching off, each bubble with its own unique roll of the dice for the laws of physics. A universe with stronger gravity, another with different fundamental particles, an infinite tapestry of possibilities. Or perhaps, our universe is the child of a black hole from a parent reality, a new space-time blossoming from the singularity of another, creating an endless cosmic family tree. These are not answers carved in stone, but tantalizing glimpses from beyond the wall of our understanding. They remind us that the ultimate mystery isn't just what we know about our beginning, but that we have the courage to ask what came before. Imagine the universe as a grand cosmic recipe. To create it, you need ingredients like matter and energy, but you also need a set of precise instructions, a series of unseen numbers that dictate how those ingredients interact. These are the fundamental constants of nature. They are the source code of our reality, woven into the fabric of space-time itself. They don't change, they don't have an explanation, they simply are. And the most remarkable thing about them is the knife-edge balance they hold. If any of these numbers were just a tiny fraction different, the universe as we know it would be impossible. The most famous constant is c, the speed of light. It's more than just a velocity, it's the universe's ultimate speed limit, the fastest that any information or causal link can travel. It's the c in Einstein's legendary equation, E equals mc squared, which tells us that energy and matter are two sides of the same coin. This one number governs everything, from the flow of time to the immense energy locked inside the heart of a star. If c were different, the very relationship between matter and energy would be rewritten. Then there's the gravitational constant, g. This number dictates the strength of gravity, the cosmic glue that pulls matter together. It's why planets form from dust, why stars ignite, and why galaxies dance in colossal spirals. G is remarkably weak compared to other forces, which is crucial. If it were slightly stronger, stars would burn out in an instant and collapse into black holes. If it were weaker, galaxies and planets would never have formed at all. The entire large-scale structure of the cosmos is held in a delicate truce by the precise value of this one number. Perhaps the most exquisitely tuned constant is the fine structure constant, alpha. This number governs the strength of electromagnetism, the force that binds electrons to atoms and allows for all of chemistry. If alpha were just a few percent different, the stable atoms that make up our world, like carbon, couldn't exist. Stars would be unable to fuse the heavier elements necessary for life. This single, dimensionless number is the master architect of all structure, from a single molecule of water to the building blocks of you and me. The speed of light, the strength of gravity, the rules of chemistry. Why do these constants have the specific values they do? We honestly don't know. Perhaps it's the only way a universe can be, governed by a deeper, undiscovered law. Or perhaps we are just the winners of a cosmic lottery, living in one of the few universes among an infinite multiverse where the numbers happen to be just right for life to emerge. These constants aren't just numbers in a textbook. They are the silent, unwavering rules that make our existence possible. Good evening, cosmic voyagers. Tonight we embark on an extraordinary journey, not just across the vast tapestry of stars and nebulae, but inward, towards a celestial body that has captivated humanity since time immemorial. Imagine, for a moment, soaring through the inky blackness, past swirling galaxies and distant suns, until a familiar, radiant orb grows larger in our view. It is our closest celestial neighbor, the Earth's silent companion, the Moon. For millennia, our understanding of the Moon was limited to what we could see with our own eyes, and, later, through early telescopes. But the true scientific unveiling of our neighbor accelerated dramatically in the 20th century. The Cold War rivalry between the United States and the Soviet Union ignited the space race, a period of intense technological competition that would propel humanity to its greatest adventure. The Soviets achieved several incredible firsts, including the first probe to impact the Moon, and in 1959, the Luna 3 mission captured the very first images of the Moon's mysterious far side. But the ultimate prize was to land a human on its surface. This goal was realized by the United States Apollo program. On July 20, 1969, Neil Armstrong and Buzz Aldrin of Apollo 11 took those first historic steps, a moment watched by hundreds of millions back on Earth. The Apollo missions were a scientific goldmine, bringing back 382 kilograms, 842 pounds, of lunar rocks and soil. Analysis of these samples confirmed the giant impact hypothesis, the theory that the Moon formed from the debris of a massive collision between a Mars-sized object and a young Earth. These rocks provided a pristine record of the early solar system's violent history and revealed that the Moon's dark plains, or Maria, were formed by ancient volcanic eruptions. But our learning didn't stop when the last Apollo astronaut returned home. In the decades since, and especially in recent years, a new wave of robotic explorers has completely revolutionized our understanding. Perhaps the single most important discovery of this new era is the confirmation of water ice. Missions like India's Chandrayaan-1 and NASA's Lunar Reconnaissance Orbiter, or LRO, used sophisticated instruments to detect significant deposits of water ice hidden in the permanent shadows of craters at the Moon's poles. This wasn't just a trace amount. We're talking about potentially billions of tons. This discovery transformed the Moon from a bone-dry world into a potential resource depot for future human exploration, a place where we could source drinking water, breathable air, and even rocket fuel. More recently, China's ambitious Chang'e program has opened new chapters in lunar exploration. In 2019, the Chang'e 4 mission achieved the historic first-ever soft landing on the far side of the Moon. Its Yutu-2 rover continues to explore this unknown territory, giving us our first ground truth data about the geology of the side of the Moon we can never see from Earth. Then, in 2020, the Chang'e 5 mission successfully collected and returned the first new lunar samples in over 40 years. These rocks were from a much younger volcanic region than anything Apollo brought back. Their analysis revealed that the Moon was volcanically active far more recently than we ever thought, forcing scientists to rethink the timeline of the Moon's thermal evolution. Astonishingly, studies of these new samples also found direct evidence of water in the form of glass beads within the lunar soil, suggesting an internal water source on the Moon. Modern orbiters have also given us an unprecedented view of our neighbor. NASA's LRO has created stunningly detailed, high-resolution 3D maps of the entire lunar surface, revealing everything from the location of the Apollo landing sites to potential resources. We have discovered vast underground lava tubes, tunnels carved by ancient magma flows that are large enough to house entire cities, offering natural protection from radiation and micrometeorites for future lunar bases. We now know the Moon has a tiny, partially molten core, experiences moonquakes from tidal stresses and thermal changes, and is surrounded by a tenuous but detectable atmosphere called an exosphere. Our silent gray companion has been revealed to be a dynamic and complex world, one that still holds countless secrets. As we plan our return with programs like Artemis, we go not just to walk in the footsteps of giants, but to build on a new foundation of knowledge, ready to unlock the next set of mysteries the Moon has waiting for us. Welcome back, cosmic travelers. We take one last look at our silent, steadfast companion, the Moon. A world of stark beauty and ancient craters, a record of our first bold steps into the universe. But our journey is far from over. Today, we leave the familiar glow of our lunar neighbor behind and set a course for a world that has ignited our imagination for centuries. A world of rusty plains and towering volcanoes. Our next destination, Mars. For our ancestors, Mars was a fiery wanderer in the night sky. Its distinct blood-red hue led the ancient Romans to name it after their god of war. For millennia, it was simply a point of light, a subject of myth, but the invention of the telescope transformed it into a place. In the late 19th century, astronomers like Giovanni Schiaparelli and Percival Lowell sketched what they believed were intricate networks of canals, leading to widespread speculation of a dying civilization, desperately channeling water across a desert planet. This vision of Martian cities and alien life, though mistaken, firmly planted a question in the human mind: are we alone? The dawn of the space age gave us the tools to finally answer that question. In 1965, NASA's Mariner 4 spacecraft flew past Mars, sending back the first close-up images. The pictures were shocking. There were no canals, no cities. Instead, they revealed a cratered, seemingly desolate landscape. Much like our Moon, hopes for finding life dwindled. But Mars had not yet revealed all its secrets. In 1971, Mariner 9 became the first probe to orbit another planet. Arriving in a planet-wide dust storm, it waited patiently for the skies to clear. And when they did, the view was breathtaking. Mariner 9 unveiled a world of colossal features. Valles Marineris, a canyon system that would dwarf the Grand Canyon, stretching a quarter of the way around the planet. Olympus Mons, a shield volcano 3 times the height of Mount Everest, the largest in our solar system. Most importantly, it revealed what looked like dried-up riverbeds and ancient deltas. The canals may have been an illusion, but water was real. Mars was not always the cold, dry desert it is today. It once had a thicker atmosphere, and liquid water flowed freely across its surface. Could life have arisen in that ancient, warmer, wetter world? To find out, we had to go there. In 2012, NASA achieved a stunning feat of engineering, landing a 1-ton, car-sized rover named Curiosity in a 96-mile-wide crater called Gale. Curiosity's mission was not to find life itself, but to determine if Mars ever had the right conditions for it. And its discoveries were profound. It found evidence of an ancient flowing stream bed with smooth, rounded pebbles just like those in rivers on Earth. By drilling into rocks that were once mud at the bottom of a lake, it confirmed the presence of all the key chemical ingredients for life. And, perhaps most tantalizingly, curiosity detected complex organic molecules, the very building blocks of life as we know it, preserved in that 3-billion-year-old mudstone. Building on Curiosity's success, the Perseverance rover landed in 2021 with an even more ambitious goal: to actively search for biosignatures, the definitive signs of past microbial life. Its landing site, Jezero Crater, was carefully chosen. It was once a vast lake, fed by a flowing river delta, a perfect environment for life to thrive and for its evidence to be preserved. Perseverance immediately confirmed that the crater floor was rich in the same kind of organic molecules Curiosity had found. But recently, it found something even more compelling. In late 2023, while analyzing a rock sample, Perseverance made a discovery that sent ripples through the scientific community. Using its advanced Sherlock instrument, the rover found a high concentration of organic molecules intimately mixed with silica and sulfates. Why is this so significant? On Earth, silica is fantastic at preserving delicate structures, including fossils of ancient microbes. And sulfates can help lock in organic matter. To find this specific combination, the right organic materials, preserved in the right minerals, in a location that was once a watery shoreline, is exactly what you would hope to find if life had once existed there. NASA calls this a potential biosignature. It's not yet definitive proof. Non-biological processes could, perhaps, create a similar signal. The final verdict will have to wait for the precious rock samples Perseverance is collecting to be returned to Earth for analysis in our most advanced labs. But with every drilled rock, with every piece of data sent across the void, we get closer to an answer. The search for life on Mars is more than just a scientific question. It's a search for our own place in the universe. Finding that life, even if it's only ancient, single-celled organisms, would mean that the spark of life is not a miracle unique to our world. It would mean the universe is likely filled with it. Our journey continues, but Mars has shown us that we live in a cosmos far more wondrous and full of possibilities than we ever dared to dream. Welcome back, cosmic travelers. We take one final look at Mars, the second destination on our grand tour, a world of rusty dust and tantalizing possibility, a silent testament to a once watery past. Its canyons and dried riverbeds will continue to call to us, promising answers to the ultimate question of life beyond Earth. But for now, our journey must continue. Our engines burn, pushing us out of the faint gravity of the red planet. We leave behind the inner solar system, the rocky worlds of our home, and set a course for the outer darkness, towards the undisputed King of Worlds. Our next destination, Jupiter. The journey from Mars to Jupiter is unlike any we have taken before. It is a voyage across a great gulf, a chasm of space that dwarfs the distances between the inner planets. For months, our home star, the Sun, will shrink behind us, and our destination will remain little more than a brilliant, unwavering star ahead. On this epic crossing, we must navigate the legendary asteroid belt. Now, popular culture would have you imagine a dense cosmic traffic jam, a field of tumbling rocks we must dodge and weave through. The reality is far more sublime and far more empty. The asteroid belt is a ghost of a planet that never was, a collection of rock and metal fragments held in orbit by the Sun, but prevented from ever forming a world by the immense gravity of the very planet we are heading towards. The average distance between asteroids here is over 500,000 miles. The danger is not from collision, but from the sheer scale and loneliness of the void. And yet, this belt is profoundly connected to our own existence. Jupiter's immense gravity acts as a cosmic shepherd, nudging these ancient rocks in their orbits. Occasionally, one of these nudges sends an asteroid careening towards the inner solar system, The very impactor that led to the extinction of the dinosaurs likely began its journey right here, set on its fateful course by the invisible hand of the gas giant. We are crossing the source of both creation and destruction for our own world. After a journey of hundreds of millions of miles, it begins. The star-like point of light blossoms into a disk, then a world that fills our entire view, its scale almost impossible for the mind to process. We have arrived at Jupiter. This is a planet built on a different framework than Earth or Mars. It is a gas giant, a colossal ball of hydrogen and helium, the very same elements that make up the Sun. In the early solar system, Jupiter grew so massive, so quickly, that it hoovered up more than twice the material of all the other planets combined. For this reason, it is often called a failed star. If it had been about 80 times more massive, the pressure and temperature at its core would have ignited nuclear fusion, and our solar system would have had 2 suns. It is a king without a crown of fire. Its sheer size is staggering. You could fit all 7 other planets inside of it with room to spare. Its diameter is 11 times that of Earth. But it's the view that truly paralyzes the senses. We see no solid surface, only an endless, deep atmosphere. Bands of cream and caramel-colored clouds, composed of ammonia and water ice, are stretched around the planet by winds screaming at over 400 miles per hour. These are not clouds in an atmosphere. These clouds are the atmosphere. And there, dominating the southern hemisphere, is the most iconic feature in the solar system, the Great Red Spot. This is not a storm, it is a superstorm. A violent, crimson eye, a hurricane wider than our entire planet that has been raging for at least 300 years. We are witnessing a weather event on a scale that defies all earthly comparison, a storm that could swallow our world whole. Jupiter is a world of extremes. Below these clouds, the pressure grows so immense that hydrogen gas is crushed into a liquid, and deeper still, into a bizarre electrically conductive fluid known as liquid metallic hydrogen. This swirling metallic ocean is what generates Jupiter's colossal magnetic field, the most powerful of any planet, creating deadly radiation belts that would destroy any unprotected spacecraft. But the story of Jupiter is not just about the planet itself. It is the center of its own mini solar system, a family of nearly 100 moons it holds in its grasp. And it is here, in the shadow of the giant, that our journey will take its next, perhaps most exciting turn. We will visit worlds of fire and ice. We will see the volcanic fury of Io and wonder at the vast, hidden ocean of Europa, a place that may hold the very life we have been searching for. Our time at the King of Planets has just begun, but we have already learned that the solar system is more magnificent and more violent than we ever imagined. Join us as we prepare to explore the children of Jupiter. Welcome back, cosmic travelers. We have arrived and borne witness to the King of Worlds, Jupiter, a colossal ball of gas and storm, a failed star that dictates the rhythm of our solar system. But the story of Jupiter is not just about the planet itself. It is the story of a celestial court, a mini solar system of nearly 100 moons held in its powerful grasp. Our time orbiting the king is over. Now our journey takes us to its children. We will visit worlds of unimaginable fire and ice, moons so complex they rival planets themselves. Our first stop is the innermost of the 4 great Galilean moons, Io. This is a world tormented by its parent planet. As Io orbits, the immense gravity of Jupiter, combined with the pulls of its neighboring moons, stretches and squeezes it like a cosmic stress ball. This relentless tidal flexing generates incredible heat, turning the moon's interior into a cauldron of molten rock. The result is the most volcanically active body in our entire solar system. And recent findings from NASA's Juno mission have peeled back the crust, confirming the source of this volcanic rage, a vast global ocean of magma churning just beneath the surface. Juno's data helped pinpoint the sources of this heat, showing us the engine of a world perpetually tearing itself apart and being reborn in fire. Io is a breathtaking but hellish landscape, a place where life as we know it could never gain a foothold. We leave the inferno of Io behind and travel outward to its complete opposite, Europa. From a distance, it appears calm, a serene white orb scarred with reddish-brown cracks. But this placid exterior hides the most exciting secret in the solar system. The same tidal forces that melt Io's rock also warm Europa's interior. But here, the result is not magma, but water. Beneath this miles-thick shell of ice lies a vast global saltwater ocean, containing more than twice the amount of water found in all of Earth's oceans combined. For decades, scientists wondered if life could exist in this dark, deep sea. A key challenge was whether the ocean was truly isolated from the surface. But exciting new research has advanced our understanding of these ocean worlds. Studies now suggest this icy shell may be more dynamic than we ever imagined, creating a potential pathway for nutrients and energy from the surface to travel down to the ocean below. This dramatically increases the chances that Europa's hidden sea could be a habitable environment, a place where life might thrive without ever seeing the light of the sun. And Europa is not alone. Its larger neighbor, Ganymede, the biggest moon in the solar system, also harbors a hidden ocean. So too, perhaps, does the ancient cratered moon Callisto. The Jovian system is not just home to one ocean world, but a family of them, each one a potential cradle for life. These tantalizing discoveries have made Jupiter's moons a primary target for our next chapter of exploration, and that future is already on its way. NASA's Europa Clipper mission launched in October of 2024 and is currently on its long voyage across the solar system. Upon its arrival at Jupiter in 2030, the sophisticated probe is designed to make dozens of close flybys of Europa. It will use ice-penetrating radar to confirm the ocean's existence, measure the thickness of the ice shell, and even attempt to fly through any water plumes erupting into space to sample the ocean's chemistry directly. The question of life on these moons is no longer pure speculation. It is a testable hypothesis. Could life exist, powered not by sunlight, but by the gravitational dance between a giant planet and its moons? Answering this would change our understanding of biology and our place in the universe forever. Our time in the courts of the king has been breathtaking. We have seen fire and ice and the profound possibility of life hidden in the deep. But the outer solar system has more wonders to show us. Our journey continues, pushing ever outward into the cold and the dark. A world of breathtaking rings and even more mysterious moons awaits.